this is a bit an asymmetric situation. You can eat, I can't eat, but I know the situation already because I have been working in the area of discrete event simulation, and they have a big conference called the Winter Simulation Conference, where it is common that they have one of the invited talks during lunch, just for economic reasons. In this way, they, they can have more program during the same day time. So, and I think it works well, in fact. So this also should work well. Just enjoy your lunch. I will bother you with some thoughts I would like to convey. Okay, so the talk, the title of my talk is Object Event Modeling. So it's about modeling. And the subtitle is A Unified View of States and Processes. And this subtitle indicates that my talk is an outlier in this program, because I think all of my fellow speakers, they are, in their work, they are concerned about data, information, and knowledge, which concerns state structure modeling. So that's the states in my subtitle. But I am also concerned about processes. And processes, of course, refer or arise through the dynamics of a system. So what I'm really interested in is understanding systems. And for understanding systems, and there are, of course, many different types of systems, and it's probably too ambitious to, to have the goal to understand all of them, but at least certain types of systems, right? And systems are characterized both by their states and by their dynamics. And this has been a difficult problem in modeling for a long time, and it still is a kind of open problem, how to have a how to obtain unified models of states and processes for modeling a system, a dynamic system. And in fact, this was mentioned in the introduction of me, that in the past I worked on the topic of agent-oriented modeling. In fact, 20 years ago, I had this paper, The Agent-Object Relationship Meta Model Towards a Unified View of State and Behavior. Now you see, it has a similar subtitle as my talk today. But I was already concerned about this issue, how to obtain unified models of the state structure and the behavior of processes, or the dynamics of a system. But at that time, I was mainly interested in understanding agent systems. And agent systems are, of course, a particular kind of systems where it makes sense to speak about their behavior. However, there are other types of systems where it does not make much sense to speak about their behavior, but it's more about the processes that they are involved in. For example, when you consider an economy as a system, I'm not sure, but I wouldn't use the term behavior for such a system, while it makes sense to use the term behavior for any kind of agent system, right? Like a biological agent or an artificial agent, but not for a system of such systems, probably. Such a system would have processes going on, but it would not really have behavior itself, right? So therefore, there is some distinction between behavior and processes, but that's not really my topic today. In fact, this subtitle, which I'm reusing today, was already a quotation of an older paper. 47 years ago, Peter Chen had this paper, The Entity Relationship Model, with a subtitle, Toward a Unified View of Data. So I was somehow quoting his subtitle and trying to make the point that we do not only need to capture data or information or state structure, but also the dynamics of systems. Okay, but I would also like to go back 40 years. 40 years ago, there was a publication called Simulation Modeling with Event Graphs. And this paper and the author Lee Schröben, he proposed the first, I would characterize it in this way, the first complete modeling language for modeling discrete processes. And he was not a computer scientist. At that time in computer science, we didn't really have process modeling. Oh no, we had process modeling, sorry, because in the 1960s, Carl Adam Petrie has proposed his Petri nets, which have been adopted in computer science for modeling distributed systems, but not for process modeling, really. So not in the sense of modeling processes of any let's say of social systems or of other discrete systems, but these process models in the form of Petri nets have been proposed specifically for certain purposes of. In fact, I think originally also about they have been intended to be used for modeling chemical processes, but then of course in computer science they have been used for modeling the technical processes of distributed systems, which is a more limited scope, right? So only later Petri nets have been proposed to be used for modeling business processes, but this is development that I find unfortunate because Petri nets do not have foundational, an ontological foundation. In fact, one of the key concepts of Petri nets, the concept of a place, is quite ambiguous. It does not have a clear meaning. And therefore, I think that using Petri nets as a process modeling language for modeling business processes and other kinds of discrete processes, such as we have in simulation modeling, is not a convincing proposal. And this is the point I would like to make, but it has not been adopted in computer science. In fact, it was largely ignored in computer science, which I do not really understand why, but possibly because it has been developed by a mathematician in the area of operations research, which is part of industrial engineering. So it was a different community, and it has been used and adopted in the area of discrete event simulation, which is a kind of interdisciplinary area where both computer scientists and industrial engineers collaborate, but still it's not really in the core of computer science, and computer scientists apparently preferred to ignore this modeling language, which is a historically an interesting phenomenon. Because this modeling language of event graphs really captures the foundation of discrete processes, namely modeling event types, modeling state changes, and modeling causation. And this forms the foundation of discrete processes. By the way, this paper has been published in the Communications of the ACM. So it was a computer science journal, but still computer scientists didn't really take it up. Okay, so here's an example of an event graph. So this is an example of an event graph. And in an event graph, you describe events in the form of circles. And the connection between events is stands for causation. So one event is causing another event, right? And this causation may be conditional. And in that case, you have a condition. So here, for example, in the first part of this event graph, in fact, this event graph describes a simple model of a manufacturing workstation as what in operations research is called a single server queuing system. But it has the same structure like a service desk, like let's say a bank teller, where people show up and have to wait for getting a service, right? So in the case of a manufacturing workstation, we have the arrival of manufacturing parts which are to be processed by the workstation, right? So we have an arrival event, so new parts arrive at the workstation, and they may have to wait in a buffer, in an input buffer, until the workstation is available for processing them. That's the typical situation of a queuing system. Which means that you have a resource which because it's busy oftentimes, and therefore when you have an arrival process, these arrived entities may have to wait, so you have a queue, you get a queue, therefore it's called a queuing system. Anyway, so the processing here of a manufacturing part, or when it would be a service desk, then it would be the processing of a customer, is described with two events, right? Processing start and processing end. So and in between you have some time, which is the duration of the processing activity. Okay, so this simple model of such a queuing system consists of these three event circles, right? Each stands for an event type. So we have arrival events, right? We have processing start events, and we have processing end events. Each type of event is associated with certain state changes. The state changes in event graphs are simple because the assumption is that the state of the system is described with the help of ordinary mathematical variables, right? So we have a set of variables. In this simple case, we only have two variables. We have a variable for the length of the queue of the input buffer here. That's the input buffer length. And we have a variable for describing if the workstation is busy or not. That's a Boolean valued variable, right? So we have only these two variables. So when we have an arrival event, then this means that the value of the length variable of the input buffer length is incremented by 1, right? This simply describes that a newly arrived manufacturing part is added to the queue, right? Okay, then we have a conditional causation relationship between the arrival event and the processing start event type, right? So when the workstation is not busy, that's the condition, then an arrival event, the occurrence of an arrival event causes or triggers a processing start follow-up event. So this means that, and we have the same pattern for the other event circuits here. For each type of event, we describe its meaning, its dynamic meaning, with two things. First, with one or more state changes. Sorry. In this modeling language, state changes are expressed in the form of variable value assignments. This is the first item that comes with each event occurrence. And the second item is one or more follow-up events, which are caused by the event occurrence, right? So here in the case of the arrival event, we have processing start events as follow-up events. While in the case of processing start events, we have as a state change that the variable busy is set to the value true. And as a follow-up event, we have processing end. Now, in a simulation model, the duration of the processing activity would be simulated by invoking typically a random variable function that computes a value for the duration, right? This is what we see here with this duration function. That's the plus sign just indicates that this is a delay. So this is the delay of the processing end event when it is caused by a processing start event. But when this would not be a simulation model, right? Then we would not know the duration, right? Then we would not have this annotation. We would just have the arrow, the causation arrow, and the time would be non-determined, how long it would take for the processing event to occur as a consequence of the processing start event. Okay, so we have a similar situation for processing end events, right? Whenever a processing end event occurs, we have these two state changes, namely the length of the input buffer will be decreased because now this manufacturing part can leave the system. And then if the length is back to 0, which means the queue is empty, then the workstation is no longer busy, right? The busy variable is set to the value false. So that's a conditional state change, right? And then we have a conditional causation, event causation arrow, only if the length of the input buffer is still greater than 0, then after the processing end event has happened, we have another processing start event, namely for the next manufacturing part from the input buffer. So this is a simple system, right? But still, it's not immediately easy to capture it. But still, I would like to make the point that this event graph modeling language, it's a diagram language, and it also has, of course, a semantics, is really at the foundation of modeling discrete processes. And it's much more natural compared to Petri net because each element has a natural ontological interpretation, right? We have events, we have causation arrows, we have conditions, we have state changes. This is what we really have in any system, and not tokens and places, which are hard to, you always have to figure out what they stand for. Of course, the transitions of a Petri net, they pretty much correspond to the events in this event graph modeling language. So again, it's an unfortunate fact of the history of process modeling in computer science that the much more natural and suitable modeling language has been ignored by computer scientists, and a more abstract language without a clear ontological semantics, namely Petri net, has been adopted. Okay, so I would like to make the point that of course the way the state structure is described in this event graph language is a bit very basic, right? Using a set of variables for describing the state of a system. That's okay, of course that's preferred by mathematicians, but that's not what we prefer in computer science, right? We rather prefer to describe the state structure of a system by modeling the objects of the system, right? Each discrete system consists of a number of objects of certain types. And when we describe the structure of each object by defining the object type with its attributes, then we have a more natural and a more readable form of state structure description, right? So therefore, these event graphs can be extended by adding objects. And then this means that objects are attached to the event circles in the form of, and then it looks very much like BPMN. In fact, I'm borrowing the visual syntax of the business process modeling notation, BPMN here, right? So the object rectangles, they have these blended corners, that's BPMN. But the point is now what we have to do is that's not BPMN. Within the object rectangles, we have to specify the state changes of the objects, which are caused by an event occurrence, right? So and now we describe the state structure of this simple system with just one object type, namely workstation, right? And the workstation has just two attributes here. So that's quite very simple, right? We have just the length attribute, called input buffer length, right? And a status attribute for capturing the fact if the workstation is busy or not, right? Or if it's available. So we still have just these two state variables, but now we have them in the form of object attributes, which is more, in some sense, more natural, right? It's more readable, because then we can describe more complex system also in this way, and then we have somehow partitioned the namespace by using object types, and that gives us a more readable state structure description. But it's still an event graph, right? So it's still in fact the same semantics, right? We still have these event circuits which come with a state change. Here it's the incrementation of the input buffer length attribute of the specific workstation that is involved in a specific arrival event. And we still have here the conditional causation of a follow-up event, which requires that the status of the workstation is available for a processing start event to follow up the arrival event, right? So it's still the same, essentially it's still the same description of the system, but it's extended by using objects in addition to events. And this is the process model, of course, right? It's not the state structure model, but this is the process model, which means that the purpose of the process model is mainly to define, if it's a design model, otherwise if it's a conceptual model, to describe the meaningful sequences of events. That's the main purpose of a process model, of a discrete process model, right? Of course, we also may have continuous process models, but that's a different story. Here, I'm only concerned with discrete process modeling. Okay, but in the process model, of course, we need to use many elements from the state structure model. So therefore, in order to be able to understand a process model, we need to understand the underlying state structure model. And this was not really needed in the case of event graphs, because the state was just described with a set of variables, right? But now, having objects, we would like to have a model of the object types that are involved in a system. So the complete model, really, the complete system model, therefore, consists of a state structure model or information model, so to speak, right, which defines or describes both the event types and the object types, because both object types and event types may have attributes. They have a structure, right? They are also information items. And in fact, this was the sense in Joao's talk, where he had examples from Wikidata where events have been described within the Wikidata ontology. So of course, in the real world, we have to capture or describe both objects and events and collect information about them. So both of them need to be modeled in an information model. But this also has been neglected, right? Because both in UML class modeling, but also in entity relationship diagrams, events have not been considered for a long time. And still today, this is not very clear to most people if events should be included in an entity relationship model or in a class model, right? Typically, they are somehow objectified. They are not distinguished between objects and events, but in fact, it makes much more sense to distinguish in an information model or state structure model between object types and event types. That's what we can do by using the categorization mechanism of UML class models, which is called stereotypes. Funny word, but still, these are categories of classes, right? So we have two categories of classes in these models, right? We have event classes and we have object classes, right? And such a distinction makes a lot of sense. And we need such a model as the basis of any process model, because the names of the object types and event types and the names of their attributes and even the names of operations, if we include them in our object event class model, how I call these types of models, are then used in the process model. We need to be able to use these names, right? And they have to be redefined in the state structure model. And then the only purpose, even if the process model is reusing or mentioning these names, but it is not defining them, the only purpose of the process model is defining the meaningful sequences, the admissible sequences of events. By relating these admissible sequences of events to state changes and via conditions. So it's related, of course, right? In the process model, this is interleaved, right? So that's why the process model depends on the state structure model. You cannot have a process model without a state structure model, even if you leave it implicit, but then you have an implicit one at the time. Okay, so I'm hurrying up. Okay, so in fact, but my last point, which I would like to make, is the semantics of these object event graphs or object event models is that for each event circle in such a diagram or event node, you can extract a rule, an event rule, how I call it, which captures the causal regularity that is inherently described in the object event graph. And then when you extract these rules, okay, this is now difficult because no, let's see, let's switch to the next one. Okay, this is better readable. Okay, okay, but no, it's good. Okay, so for each of these event circles in the diagram, right, I can extract such a pattern where we have the event occurrence of one event type here, processing start events, right, and then we have a state change which is caused by this event occurrence, and a follow-up event which is caused by this event occurrence, right? So this can be somehow formalized, described textually in a kind of rule, which I call event rule. And these event rules correspond to transition functions of a transition system, of a state transition system, where the states of the transition system correspond to interpretations of predicate logic language. In fact, it's similar to the database states, to the states of a database, which somehow correspond to interpretations of the language, of the predicate logic language on which a database is built upon. So so that's the formal semantics, right? So each event rule, which is described implicitly in the object event graph, expresses a transition function, which can then be by forming this set of all these transition functions, you obtain a state transition system, and that state transition system is the semantics of the process model. This consideration can be extended to also looking at activities, because that's what you normally want to have in process charts, right? In flow charts, you want to have activities, and an activity is obtained by merging a pattern of two events, where one corresponds to an activity start event and the other one to an activity end event. And then whenever you have such a pattern in an event graph, you can replace it by using an activity rectangle. So activities are definable here on the basis of events. So the conclusions I would like to make is considering both business objects and business events, both in information or state structure modeling and in process modeling, is very natural, but has not been done traditionally. It has been neglected both in information modeling, where events have been not considered much, and it has also been neglected in business process modeling, where objects have not been considered much. Object event modeling, which I propose, provides a complete computational picture of the states and processes of discrete systems based on the computational concept of event pools, which capture causal regularities. Thank you for your attention.